We've talked about how at different points in an electric field you have differences in electric potential, and that the word for electric potential is voltage. We haven't talked yet about the motion of particles due to these differences in electric potential. And so now we're going to talk about the motion of charge in circuits. So the first thing we have to talk about is what does it mean as charge, or how do we describe charges in motion? And we're going to define a new quantity, the current, and we'll call it I. I don't know what the I stands for, but that's what people always use for current, and probably some kind of Greek or Latin thing. And it is equal to the rate of charge passing through some point per unit time. So it's like the speed of charge moving past a point you can think of it as like a wire, a conductor. The SI units for current, based on this equation, you can see that you can give the units as coulombs per second. That's the units of charge divided by units of time. But this is going to be a really important unit for us, and so we're going to give it its own name just to shorten it a little bit. It's called the ampere, and people just call it an amp. So we'll just describe it as amps, and you use the abbreviation A for that unit. Current can only flow through a complete circuit. And a circuit is made up of two things. Nodes and elements, circuit elements. So this is what a circuit diagram looks like, and I'll tell you what these elements mean soon. Okay, but the nodes are all the places, so a single node is all the places you can reach without passing through an element. So this is one node. Okay, it looks like these nodes are represented as if they're wires. And then this is the other node. Okay. And the two elements are this and this. So that's the entire circuit. You're either in a node or you're on an element. And solving a circuit means finding the current and the current direction at each element, and finding the voltage and the polarity, which is like the voltage direction at each element. So you've solved the circuit when you know the voltage and the current with their directions at every element. The nodes, so that's the stuff in green in the picture above, are all the, I'm going to just call it wire, but it's all the wires in the diagram that can be reached without passing through an element. And nodes are important because on a node, the electric potential is the same everywhere on that node. Electric potential is the same everywhere on that same node. So if you're on a single node and you put a voltmeter to measure voltage, to measure a difference in electric potential, at any 2 points on the wire in a single node, that voltmeter would read 0 because those electric potentials are the same, and so the electric potential difference is 0. The voltage is 0. And then the red are the elements. Those are the things that where we want to find the current and the voltage with the directions. The first two elements that we'll work with, so this is what we're talking about in this lecture, are batteries and resistors. And that's why, so the title of this lecture is Resistive Circuits. Besides batteries that we need to get the current moving, the only other element type we're going to see for now are resistors. A battery has an electric potential difference at the two terminals. And so, and the SI units then for that potential difference is volts. And so here is sort of a pseudo drawing of what it looks like. If you have a battery, you have a positive terminal on this side, a negative terminal on this side. It gives you some unit like 12 volts. And what that says is that the potential difference is 12 volts, or the electric potential is 12 volts higher on the positive side than it is on the negative side. So if you took a voltmeter to measure voltage and put the positive on the positive terminal of the battery and the negative on the negative terminal of the battery, it would tell you 12 volts. If you switched it around, it would tell you negative 12 volts. A resistor is something that limits current. Thanks. So every resistor you put in limits the current flow through that wire. And the resistance is equal to the difference in electric potential, the voltage, divided by the current. One thing that is going to be important for us in determining directions is in a resistor, the voltage drop is always in the direction of the current flow. Okay, so if you have a resistor like this is the schematic symbol for a resistor. And if you know that current is flowing this direction through the resistor, then you know that the polarity of the voltage is the positive on this side and the negative on this side. Okay, so I'm going to start writing the voltage symbol as just a V instead of a delta V. But remember that this is voltage. So what this is saying is the electric potential on the positive side of this element is V volts higher than the electric potential on this side. This is a difference in electric potential. And this says that since we know the current is going from left to right, we know that the drop, the direction from positive to negative voltage, is also from left to right. And if you had a resistor like this, and the current was going this way in this circuit, then you know that the polarity is like this. Okay, that's going to be an important thing for us. In order to get sort of an intuitive sense of how these circuit elements fit together, think of a battery as a fluid pump. And a resistor as a constriction in the pump. Okay, so I said that a resistor limits flow. We're going to relate the current to fluid flow. The battery is the thing that makes the fluid flow. It's the pump. The resistor, constrictions in that pipe, limit the rate of that flow. And so you can think of a circuit as like you have a pump here that causes a pressure difference, a high pressure on this side and a low pressure on this side. And that causes water or whatever fluid to flow this direction through the pipes. And that flow is limited by constrictions in the pipe that slows that flow down. Okay, so this pump, think of the battery that way. This constriction, think of that as a resistor. And the most important use of this way of thinking about it, and I'm going to give the equivalent, the corresponding circuit schematic. So this, in this case, the battery is always shown by a long line and a short line. The long line is the positive terminal of the battery, then the short line is the negative. And this is a resistor on top. And so what this does is it produces a flow of current in the direction, out of the positive terminal of the battery. And it goes around, and this constriction, this fluid flow is going to keep going this way. That means that the potential difference has this polarity. Okay, so the most useful reason to think of this analogy, so this fluid analogy, is really helpful for guessing the directions of the current and the voltage. Helpful for guessing the direction of the current and the polarity of the voltage. And we're going to see that in doing any calculations, the first thing you have to do is just guess these directions. Your guesses don't have to be right, but it saves you a little bit of extra trouble if your guesses are right. And thinking about it as a pump forcing fluid through pipes makes it a lot easier to guess correctly. So now we're just about ready to start solving circuits. And there are three equations that we're going to use in solving circuits. The first one is called Ohm's law. And it says that, well, I've already showed you this in a different form, but it says that voltage at a resistor is equal to the current flow through the resistor times the resistance. Where the SI units for resistance are, you can see that that would be volts per amp, and we give that its own name, ohms, and it's represented with the Greek letter omega. Okay, so what this says, the first equation, says that we don't really have to think about the voltage of the resistors to start with, because if we can find the current through the resistors, we can just multiply by the resistance and that'll give us the voltage. Okay, so that's the first one. The second one is called Kirchhoff's current law. And it says that at any node, the total current flowing into the node is equal to the total current flowing out of the node. And then the last one says, well, this is called Kirchhoff's voltage law. And it says, in any complete loop around the circuit, so any path you can take around the circuit that gets you back to your starting point, the sum of voltage rises is equal to the sum of voltage drops. So I'm going to do two examples, a really simple example and then a more complicated example. And in both of those cases, I'm going to use the same approach, or the same sort of set of steps. So first, I'm going to represent all the voltages in the resistors. So represent the voltages Okay, so the first thing I'm going to do is guess my directions. Using the water flow analogy, or the fluid flow analogy. Sometimes there are really complicated cases where this doesn't give you a clear idea of what's going on. It's just hard in those cases to come up with perfect guesses all the time. But this will usually lead you in the right direction. And like I said before, if you guess wrong, you'll get a negative answer, and that'll tell you the real direction. So I'll do an example to show that too later on. So guess the directions using the fluid flow analogy. Second, use Ohm's law to represent each voltage across a resistor as the resistance times the current for that resistor. Third, I'm going to use Kirchhoff's current law to find current equations at the nodes. So I'll say current equation for each node. And it happens pretty often that you're going to get repeats of the same equations. So if you see repeats, you know, two identical equations don't help. So just leave off any repeats. So if you see repeats, just ignore one of them. And then finally, we'll use Kirchhoff's voltage law and that'll give us any additional equations we need. So this will give us the rest of the equations that we need to solve the circuit. Okay, so the first example is as simple as a circuit can be. So I'm going to have a battery here and a resistor here. The long side of the battery is the positive, the short side is the negative, and I'm going to say that this battery is 20 volts, and this resistor has a resistance of 100 ohms. And we want to solve this circuit. Okay, well, the first step is we're going to use the fluid flow analogy to guess directions. It's easy in a case like this. If you think of this battery as being a high pressure on the left and a low pressure on the right, and the fluid can't flow through the battery, it can only flow out of the high pressure side. So we know that the fluid would flow this way, and I'll call that current I battery. And if the fluid is going this way and it hits a constriction, the current, the flow is still going to go this way, so I'll call this IR. And then the polarity always has to be, so we have to go plus to minus in the same direction as the current at a resistor. So there's the plus, there's the minus, and now we've chosen our directions. Okay. Now I'm going to use Ohm's law to replace the voltage. So I could call this voltage drop for this resistor VR, but I'm going to just replace it right away with using Ohm's law as 100 times IR. So it's the resistance times the current. And now I'm done with that. So I've done the first two steps. And now I'm going to Kirchhoff's current law. And at this node, we have one current flowing into the node, the way we've assumed the directions, IB. And we have one current flowing out of the node, IR. And whether it's going into or out of just comes from the directions of those arrows and where they fall on that node. Okay, so we know that IB, the one current going into the node, is equal to IR, the one going out. Now if we go to the other node, I'll do this one in blue. What does that one say? Well, now it says that IR is going into the node and IB is going out of the node, but we get the same equation. IB and IR are the same. So I'm just going to leave that off. And now, you know, you can look and see if we can solve this yet. We know those currents are the same, but we don't have a way to calculate either one of the currents. So we're going to need one more equation from Kirchhoff's voltage law. And that says add up all the voltage rises. Those have to equal all the voltage drops. Okay, so I'm going to go around this loop clockwise. It doesn't matter which way you go. You can go either direction. And so going clockwise, we have a voltage rise of 20. And we have a voltage drop of 100 times IR. And now we can, piece by piece, this is a system of equations that you have to solve together by substitution. And so this one says that IR is equal to 0.2, and this is in amps. And since we know that IB is equal to IR, this is also the current coming out of the battery. Since this is positive, we guessed those directions correctly. And now finally, we already have the voltage at the battery, but we need the voltage here, and that voltage is 100 times IR. So the voltage at the resistor is equal to 100 times 0.2, or 20 volts. And so now we can draw this again with everything filled in. Since everything came out positive, the directions are the way we drew them in the first figure. So we have 20 volts in that direction. We have a current of 0.2 amps in that direction. Here we have a voltage drop this direction of 20 volts and a current of 0.2 amps. And there it is, a solved circuit. Now I'm going to do a more complicated example. So let's say in this case, our battery is here, and we connect to a resistor there, and a resistor there. And another resistor there. So we have 3 total resistors. And this battery is 15 volts. This resistor is 50 ohms. And then we have 10 ohms here. Let me put that on the other side. And then we have 20 ohms here. And we want to solve this circuit. Okay, well, let me copy this so I can draw on it. The first thing we're going to do is use the fluid flow analogy to think of the directions. Okay, well, this battery has the positive side down, so that's this way, and that means that if we were talking about pressures, this pump would be forcing flow out of the positive side. So this is the direction of the current at the battery. And then if you think of this as fluid flowing down from the battery, down from that pump, it will be going to the right when it gets to the 50, and then it'll be going up as it goes through both the 10 and the 20, and then it'll return along the top back to the other side of the pump. Okay, so we have a direction and a polarity like this, and I'll call this I-50. It doesn't matter what you call these, you just have to keep them straight. And here it's going to be going up. This is our I-10, and our polarity is this way. And at the 20, it's going to be going up. So that's our I-20, and the polarity is this way. And now for the voltages at these resistors, we're going to use Ohm's law. And so I'll do that step in green. So the voltage at the 50 ohm resistor is 50. I said green. 50 times I50. At the I10, this is the resistance, 10 times I10. And at the 20 ohm resistor, we have 20 times I20. And now we'll go to Kirchhoff's current law. So the first node, let's take the node that connects the battery to the 50 ohm resistor. I'll circle it, but then I'll erase it. So that's the node we're talking about. You can see the current IB goes into that node. The current I50 goes out of that node. And so we have that IB is equal to I50. Next, we'll go to this node. Remember, a node is all the wire that you can get to without going through an element. So all of that gray is a single node. I didn't touch any elements to do that. So going into that node, we have I50. Going out, we have I10 and I20. So I50, whoops, let me get that all erased. Okay, so now we have, this should be I50. So I50 is equal to I10 plus I20. And now the last node is this big one. You can see that that says going into that node, we have I10 and I20. Going out, we have IB. That looks like a new equation, kind of, except it's this second equation if we just substitute the first one into it. If you don't see that, it's really not a problem, but I'm going to leave this one off because our two first equations already tell us that. Okay, so do we have enough yet to calculate the currents? You could think of it as we have 4 unknowns and we have 2 equations. So we know we're going to need at least 2 voltage equations. So the voltage law. First, I'm going to do the left loop. I'm going to start at the node right above the battery. So we have a voltage rise of 15. A voltage drop of 50 I50. A voltage drop of 10 I10. And then if we keep following that loop, we get back to the starting point. So that's one of them. And then for our second equation, we could use the big outer loop, or we could use the small right loop. I'm going to use the small right loop. It'll just have fewer variables in it. So if I start my loop here, we rise 10 I10. And then we drop 20 I20. And now we have the variables IB, I50, I10, I20. That's 4 variables. We have 4 equations. As long as that system of equations isn't redundant in any way, we can solve this by substitution. So I'm going to just start substituting things. I'm going to put IB in anywhere I see I50. So we have IB is equal to I10 plus I20. And then we have 15 is equal to 50 IB plus 10 I10. And then we have 10 I10 is equal to 20 I20. Okay, now I'm going to substitute, I10 is equal to 2 I20. So I'm going to take this system and rewrite it again down here. Each time I do this, I should be getting rid of one equation. And so this says IB is equal to 2 I20 plus I20, so 3 I20. And then we have that 15 is equal to, I'm going to replace this I10 with 2 I20, so this is 50 IB plus 20 I20. And now the last step, we have a system of 2 equations for 2 variables. And so I'm going to replace IB with 3 I20. And so we have 15 is equal to 150 I20 plus 20 I20. So 15 is equal to 170 I20. And that gives us our first one, that I20 is equal to 15 divided by 170, or 0.088, I'll keep a bunch of digits, 235 amps. And now we can go and start, unraveling this whole mystery once we have one of these currents. As long as you haven't made any mistakes, every single equation on your page is a true equation, so you can just look for the easiest ones. We have I20 is this. Well, here this says IB is 3 times that. And so the current at the battery is 0.264706 amps. I10 is equal to 2 I20. And so that is equal to 0.176471 amps. And now we're just looking for a way to calculate I50. Well, I50 is equal to IB. So I50 is also equal to 0.264706 amps. And once I put those in, all the voltages, we know the voltage at the battery, the voltages at the resistors are just the formulas in green, where we just plug in those currents we just found. So, as a final answer, our battery has that polarity. Our current at the battery, since everything came out positive, is in the direction we guessed. So I'm going to call that 0.26, just rounding. Then at this resistor, the 50 ohm resistor, we have a current of 0.26 amps and a voltage of 50 times that 0.264706. So 13.24 volts. And then at this one, that's the 10 ohm resistor. We have a current of 0.18 if I round, and a voltage of that current times 10. So that is 1.76 volts. And then the last one, we have a current going this way of 0.088. And the voltage has the polarity we guessed. And the voltage is the current times 20. And so this is also 1.76 volts. Now I'm going to do an example where I guessed the direction wrong. So what if you guess a direction wrong? So let's take, I'm going to do somewhere in between the two examples I just did. Let's say that we have a circuit like this with a resistor there and a resistor there. Let's say that this is a 12 volt battery, and let's say that this is 5 ohms here and 10 ohms here. And we want to solve this circuit. Okay, so the first step is that you use that fluid flow analogy to guess the direction of the different currents, and therefore the voltage is the voltage polarity. So let's say, what color did I use before? So I'm going to do these in red. So let's say that we assume that the current is going to go this way from the battery, and that's right. But let's say that somehow we think that the flow is going to go this way along the 5, with the corresponding polarity. But then let's say we think it's going to go that way and then S back on the other one. It's not going to do that. But let's say this is our I-10. And then our polarity has to be that way. I drew those on the wrong one. Let me move those. But think about the way fluid would really flow if you did this. It would go out the pump to the left, and it would go in the left side of the constrictions on both of these, and then the flow would join here and it would go back. But we're assuming that instead it goes this way, and then this way. And we're going to see how the math shows us that we guessed wrong and then allows us to correct that. So I'm going to start by representing the voltages. We know that here the voltage is, I'm going to get these out of here just for a little more space. But we know that in the 10 ohm resistor, if the current was going to the left, then the voltage drop would be to the left, and the voltage would be 10 times I10. And on this one, if we assume it's going to the right, the voltage drop would be to the right, and it would have a magnitude of 5I5. And now we'll go to Kirchhoff's current law. So first I'm going to use this node. And you can see going into that node is IB. Going out of that node is I5. And then this is wrong, but we're still going to assume that I10 is going into the node. Okay, and that's how I'm going to put it in my equation. So we have 2 going into the node. We have IB plus I10, and those are equal to I5. And now we'll go to the only other node, which is this one. And that says going into the node, we have I5. Going out of the node, we have I10 plus IB. That's the exact same equation as this. So I'm going to leave that alone. And now we have one equation for 3 variables. That means we need 2 equations from Kirchhoff's voltage law. So the first one, we know the polarity of the battery is that way. So let me do that small loop, that small bottom loop. And so we have a voltage rise of 12, and that's equal to the voltage drop of 5 times I5. And then for a second one, we could use the outer loop, or we could use the small top loop. I guess I'll use the outer loop in this case, but I don't have any reason for that. I'm just going to do it arbitrarily. So we have a voltage rise of 12, and we have a voltage. Now, the way I have it guessed, my wrong guess, says this is another voltage rise if we're going clockwise around this outer loop. You don't have to go clockwise. You could go counterclockwise, and then it would say that you have 2 drops. The equation would essentially be the same. But clockwise, we have a 12-volt rise and then a 10I10 rise. And no drops. So now we have 3 equations for 3 variables, and we can start filling stuff in. This allows us to calculate I5. So I5 is 12 divided by 5. So 2.4 amps. And this one allows us to calculate I10. Now here's where that mistake shows up. I10 is going to give us a negative value. So I10 is equal to negative 12 divided by 10, which is negative 1.2 amps. And so that negative tells us our answer has a magnitude of 1.2 amps, and it goes the opposite direction of what we drew. And now finally, IB, I go up to the current law equation. IB is equal to I5 minus I10, which is 2.4 minus 1.2, so 3.6 amps. Since we only have one negative, we only have one wrong direction. And now I can redraw this. And we have the positive and the negative. The current from the battery is 3.6 amps. This one, we guessed correctly the direction, and that current is 2.4 amps. The voltage is 5 times 2.4, which is 12. And this one, since we got a negative current when we assumed it was going to the left, now we know it's going to the right. Its value is 1.2 amps. The drop has to be in the direction of the current. And we have 10 times 1.2 is 12 volts. Cool, right? It's self-correcting if you follow the steps right. One thing that you can sometimes use to simplify this stuff is the idea of series or parallel resistors. And I'm not really going to emphasize these with my questions, but I want you to at least recognize these. Series resistors are two resistors that share one node. Come back. Okay, they share one node and nothing else shares that node. And they don't share their other node. And so an example of resistors in series is something like this. Okay, you have one resistor here and one here. They share the node that connects them, but they don't share the other nodes. Series resistors have the same current but different voltages. And if you package series resistors as a single thing, so if you think of them as a single resistor, hold on, electronics. So if you treat them as a single resistor, Like imagine putting electrical tape around the whole section that contains both of those and thinking of it as a single resistor. Then the equivalent resistance, R equivalent, is equal to the sum of the two resistances. Okay, the second type is parallel resistors. Parallel resistors share a node on each side. Okay, so an example of parallel resistors would be this. This is R1 and this is R2. And you can see that on the left they share a node and on the right they share a node. It doesn't matter what else shares it. So this one can be shared. These nodes can be shared by other things. By other elements. And if you treat these as a single resistor, there's a different relationship. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. Okay, that's the easiest way to remember it. Mathematically, you'd have to get common denominators and stuff, and it comes out to that the equivalent resistance is equal to R1 plus R2. Sorry, I did my denominators thing wrong. R1 times R2 divided by the sum of R1 and R2. Okay, so let me show you how people take advantage of this. So let's say that we have a 24-volt battery. And it's connected to a resistor there. And it's connected to a resistor there. And let's say that this is 20 ohms and this is 40 ohms. And let's say instead of solving this whole thing, we just want to figure out what's the current being drawn from the battery. So we just want that current IB. Well, first we have to identify whether these are in series or parallel. I sort of purposely drew it in a funky configuration, so you have to think about the definition and not just look for something that looks like parallel. But let's identify the nodes, and that's how we'll identify these. So there's one node here, and you can see that those two resistors share that node. And there's another resistor. Come on. The other node is here, okay? And so you can see that the left of the 20 ohm and the top of the 40 ohm share one node, and the right of the 20 ohm and the bottom of the 40 ohm share another node. So even though they don't really look like they're parallel the way you think of parallel, these are parallel resistors. And so now we can replace these parallel resistors with a single equivalent resistor. Okay, so the equivalent resistor to this is 20 times 40 divided by 20 plus 40. And that's 800 divided by 60. Or 13.3 repeating ohms. Okay. And as an aside, parallel resistors, their equivalent resistance is always lower than either of the two because it gives the current more options to move through. Okay, so now we can set this up as a single equivalent resistance. Okay, so we have 24 volts. We know that our current is going to be going this way. This resistance now, we just have a single one that's 13.3 ohms. The current's going to go this way. The polarity is this way. And it just, now, if all we want is that current being drawn from the battery, this is just a really easy problem. The current, well, first let me write in the resistance, the voltage here is going to be 13.3 repeating times IR. Then we'll go to Kirchhoff's current law, and it says that IB is equal to IR. And then we'll go to the voltage law, and it says 24 is equal to 13.3 repeating IR. So IR is equal to 1.8. And IB is equal to that, we already knew, so IB is 1.8. And so in certain cases, this can save you a bit of time. The last thing we have to talk about is a more realistic model of batteries. We're not going to use this typically either, but it's important to understand this as a way to understand how batteries work. And I think the way to think of it is, think of the battery that you use to start your car. It's this giant thing, but it's only 24 volts. You might think that it's giant because it needs to produce a lot of voltage. 24 volts isn't really that much. You know, your wall voltage is 120 volts. And so you have the negative terminal and the positive, and this is what starts your car. So you might ask yourself, well, I know that those little batteries at the drugstore, you know, you can get 9-volt batteries at the drugstore. And if you hooked up 3 batteries, 9-volt batteries in series like this, where in every case you took the positive terminal of one, put it to the negative of the other, positive to negative, okay? This together has a voltage of 27 volts, okay? So could this collection of 3 little batteries that you can hold in your pocket start your car? It would not be able to. And the reason is this big battery, this big car battery is very good at providing current at that voltage, a lot of current. You need a lot of current to start your car. These are 27 volts when there's no current, but the voltage drops down really fast as the current gets bigger, and you can't provide nearly enough current to start a car with these. And so a more accurate model of a battery is that every battery has an internal resistance. And that internal resistance is related to how much current the battery can provide while still having a certain voltage. Okay, and so the way it works is this. The voltage of the battery is equal to this Greek letter epsilon minus the internal resistance times the current. This epsilon is the electromotor force, EMF people call it. And that is the voltage at 0 current. This epsilon is called the EMF, the electromotor force. And this is the voltage that the battery provides at 0 current. This lowercase r is called the internal resistance. And that's provided in ohms as if there's a resistor inside your battery. And then I is the current being drawn from the battery. So let's see how this works in an example. So let's say that we have a circuit like this. We have a battery, and let's say this is a 9-volt battery. Okay, so let's say that this is a 9-volt battery, and let's say we have a 20-ohm resistor. And now the voltage of the battery is 9 volts when there's 0 current, but let's say that our internal resistance is 2 ohms times the current, okay? And we want to calculate for this circuit, you know, we want to solve this circuit. Well, if it was really providing 9 volts at whatever current, then we would have 9 volts in this resistor, and the current would be 9/20ths of an amp. Okay, but this battery can't provide that much current very easily. And so we're going to, our positive is this way, and our battery current is like this. And then these are the directions. The voltage here, if this current is IR, This voltage is going to be 20 times IR. And now we can use Kirchhoff's current law. And that says that IB is equal to IR. And then we'll use the voltage law. And that says that, so this is not going to be 9 volts. It's going to be 9 minus 2 times IB as the voltage going into the node, or as the, this is a voltage rise, and then the voltage drop is going to be 20 times IR. We know these are the same, so I'm just going to replace IR with IB. And so what we get is that 9 is equal to, in this case, 22 IB. We have this increase in resistance due to the battery's inability to provide such a big current. And so the current that can be produced here is not 9 divided by 20, but it's 9 divided by 22, or 0.409 amps. Now, one other thing that we can answer with this is, what if a short circuit happened in this circuit? And instead of, so let me draw this again. So let's say we have this battery down here and this resistor. But now, instead of the circuit working as it should, a connection is made between these two parts. Okay? Well, now notice that the resistor has, this is the same node at both ends of the resistor. And so there's no voltage across the resistor, which means there's no current. And so it's like that resistor isn't even there. And so what happens now is, if we have this battery and then no resistors, what's the current that this battery produces? So our voltage is 9 minus 2I, okay? And our current I is this way. If there was no internal resistance in the battery, this would be an infinite current. But our battery can't provide an infinite current. So this internal resistance idea allows us to calculate the maximum current. And so the voltage law in this case, the current law doesn't give us anything useful, but the voltage law in this case tells us that 9 minus 2I, voltage rise, is equal to, there's no voltage drops. And so 9 is equal to 2I. And so I is equal to 4.5 amps, which that's probably lower than a realistic internal resistance. So that's still a really big current, but it's a lot smaller than infinite current.